Hello, I would like to thank you all for attending this presentation. I plan to be brief. My name is Ricardo Molina. I am a PhD student at the Renewable Energies Institute from the National Autonomous University of Mexico. Today, I'm going to present you our research about distinct configurations of vertical air-to-air heat exchangers. I will divide this talk into three parts: an introduction, followed by the methodology, and finally a conclusion. I would like to start reminding you that electrical energy consumption for cooling and heating buildings reaches 40% of total energy consumption in the world. To change this, several researchers have studied and demonstrated the potentiality and benefits of the use of geothermal energy to cooling and heating buildings. Although research results have been encouraging, some issues are necessary to attend. One of them is the available location to install exchangers in urbanized areas, because this topic has been neglected in some experimental or numerical works. To compensate this obstacle, vertical deep wells have been drilled, leading to an expensive initial cost. To attend this problem, in this work, three distinct configurations of vertical air-to-air heat exchanger have been analyzed. Also, an economical comparison between a single deep well against several shallow wells has been done. On the other hand, referring to the methodology, I will start explaining that the experimental section of this work was done in Temixco, Morelos, Mexico. Tests were carried out during March, April, and May 2020. During these months, the weather is warm and humid, approaching 40 degrees Celsius at noon. Vertical air-to-air heat exchangers were installed in the Renewable Energies Institute using a manual drilling machine. The available area to install them was 9 square meters, 3 meters by side. In this area, 9 wells among 2.75 and 2.90 deep meters were dug. The difference between depth was due to soil composition. To backfill wells, the same excavation material was used, preventing the use of foundation remains, which could fracture pipes. The 9 exchangers were done with 2 and 3 inches PVC pipes. The exchangers were connected in series to operation. Ducts that connected vertical exchangers in each well has 1.4 meter in length and was thermally isolated. To move air into the tubes, a fan was located at the inlet of the exchangers. Instrumentation of the exchangers was done with 9 tight T thermocouples, 4 of them to measure air temperature inside the pipes, and the other 5 to measure thermal disturbance in the surrounding soil. Thermocouples were previously calibrated in a constant temperature water bath. To measure the effectiveness of the exchanger, the coefficient of performance, also known as COP, was used. In total, 6 tests were completed. But before that, it's necessary to mention that all temperatures are expressed in degrees Celsius, the total length in meters, speed in meters per second, and, as is known, the coefficient of performance, COP, is adimensional. The first one was done on March 23rd in the 3 inches exchanger, with a total length of 11.8 meters and an airspeed of 5.4 meters per second. The temperature difference between inlet and outlet was 7.3 degrees Celsius, while COP was 7.3. The thermal disturbance measured at 15 centimeters of the external wall of the tube was 1.5 degrees Celsius. The second one was carried out on March 24th. In this test, airspeed was reduced to 4.8 meters per second, giving a result of 7.5 degrees Celsius of temperature difference. The calculated COP was 6.7, and thermal disturbance at 15 centimeters of the first pipe was 1.6 degrees Celsius. The third test, which continued for 2 days, the total length of the exchanger was increased to 18.2 meters, with an airspeed of 4.8 meters per second. As a result, COP calculated was 8.5, thermal disturbance 0.8 degrees Celsius, and a temperature loss of 9.4 degrees Celsius. The fourth one began on April 2nd. In those days, the environmental temperature reached 39 degrees Celsius. To this inlet temperature, the average COP calculated was 7.1 and the thermal disturbance was 1.7 degrees Celsius. During the fan operation, a maximum temperature difference of 11 degrees Celsius was achieved. The fifth one began on April 15. In this test, the 2 inches exchanger was used with 18.2 meters of total length. The measured air velocity at the outlet of the exchanger was 2.2 meters per second. During experimentation time, it was observed that 92% of total temperature difference was accomplished in the first well. Actually, a gain of temperature due to problems with thermal isolation was observed. The last one was conducted since May 4th. In this test, the 25 cm separated exchanger was used. In those days, the environmental temperature dropped to 37 degrees Celsius. COP was 5.7 with a temperature difference of 6.3 degrees Celsius. The total cost, including machines, tools, and workforce, was $710. On the other hand, a budget was requested from some companies. The budgets include a 10 meters deep well with a diameter of 50 centimeters. In response, the cost of a single well was $3,000. Finally, the partial conclusions of this work are the following. Increased airspeed improves COP due to mass flow rate, but cooling gain is not significant. Extending total length from 2 to 3 volts does not mean improving COP because the main thermal exchange is done in the first 2 wells. Increasing the inlet temperature has a direct connection with the thermal disturbance that occurs around the pipes. Raising separation between pipes in the same well decreases thermal disturbance, but does not have influence in outlet temperature. Changing the diameter from 3 to 2 inches enhances temperature difference, but COP drops off, which could be rectified using more 2 inches exchangers. Digging several shallow wells is better and cheaper than a single deep well. And that brings me to the end of my presentation. Thanks for your attention.